Okay, so hey guys. Okay, it's been a while. It's been a while. So, welcome to the channel. Now, this is not gonna be a normal video, and mind you, I've not uploaded onto YouTube since COVID. So, yeah. Now, the first video back on this channel after a really long while, except now it's a school project. So, um, hopefully to my chem teacher watching this, I hope I literally do I hope I did everything well. So yeah, I'm gonna try. I was like original though, I was gonna try explain organic chemistry, give you a quick rundown, all types of stuff from the structures to like applications within 8 minutes, or basically one lap of the Nurburgring. And it's safe to say I really didn't do that. So yeah, but regardless, I thought this will be really fun. And meanwhile, I have a nice background for like for this one really good game I've been loving, and also it is technically relevant to organic chemistry. Yeah. But yeah, anyways, so yeah, y'all just sit back. Hopefully you gain something from this. Obviously it's not gonna cover everything though. That's something I'll definitely add. It's not gonna cover everything, but let's get into it, right? So, organic chemistry is basically the study of carbon compounds. Yeah, that's basically it, right? Though we have the exceptions here, right? So the exceptions to this. So like organic compounds, the exceptions are gonna be any oxides of carbons, carbonates, cyanides, and carbides. But for anything else that's a carbon compound, it's gonna be really, it's gonna be organic, right? So you focus on carbon because it forms four covalent bonds, allowing for chains, rings, and multiple bonds, spheres, whatnot, right? You're gonna mostly look at chains and probably a bit of rings, mostly chains, right? So isomers are basically molecules or basically compounds with the same formula, the same chemical formula, but a different structure. So a great example will be C4H10, right? So that can be either butane, a straight chain, or 2-methylpropane, which is a branched chain. And also, something you have to know is structure changes the boiling point. Okay, so we're gonna get into the aliphatics and then later on into aromatics. But let's begin with aliphatics, right? So with the aliphatics, generally, for the naming rules, you have to number one find the parent chain, and then count the longest number of like the longest chain, right? And then you have to number for the lowest sum, right? And the reason you have to number for the lowest sum is basically for the branches. The branches have to have like a really small number, like the lowest number possible, right? So that's why you number the carbon atoms in that way basically. And then number three, you list the branches alphabetically in addition to the lowest number. So for the alkanes, they're saturated compounds. They only have like single bonds only, right? And their suffix is ane, right? Alkanes really simple to name, basically. Yeah. So we have like two examples. We have ethane, and then we have 2,3-ethyl hexane, right? So I'm gonna give you like a nice table or two, actually. Yeah. So for one of them, it's gonna be for the branches, for like the branches numbers, basically. And for the other one, it's gonna be the number of like carbons in the main chain, like for the prefix, right? So anyways, let's get into alkenes. Alkenes are unsaturated. They feature at least one double bond, or a few more maybe, but mostly, yeah. And the suffix is gonna be ene, right? So it's gonna they are so for this one's gonna be slightly different in that when when you when we have like, so you have to number the double bond as the lowest number. That's the slight difference when it comes to these, right? So we're gonna have two examples, right? We're gonna have ethene and we're gonna have pent-2-ene. So notice where the double bond the double bond A's in the pent-2-ene, right? Hence why we give it the number in between, unlike alkanes where it's just the normal name, right? So for alkynes, it's literally the same thing, except now the suffix is going to be Y and E, right? Same rules as alkenes, except just that. Yeah, same rules overall. So we have something called cyclic hydrocarbons, which basically just add on to this. So they can be like, we're gonna have two examples like cyclobutane, cyclohexene, and we have a whole bunch of these. We have they're all over the place, and usually like you add the prefix cyclo to the parent name. That's the only addition you need to make to it, right? So anyways, let's get into the aromatics, right? So for aromatics, we focus mostly on the benzene. So the benzene is C6H6, and basically it has alternating double bonds. So like this is what it's gonna look like. And don't confuse this with cyclohexane, hexene, whatever, right? Yeah. Okay, so the exceptions now with the naming. The naming is, let's say, relatively simple, right? So, for example, the exceptions is, if the side chain is complex, for example, it has a double bond, the benzene becomes a branch. So in that case, you don't call it a benzene, it just becomes a branch, and then you use like the branch and then the parent name, right? So we're gonna use like the example here will be like something like 2-phenyl-but-2-ene, right? No, but if the benzene is the main chain thing, main ring, it's gonna be like the parent name, and then like any branches to it, you're gonna add like now the alkyl group, like it's gonna be methylbenzene, for example, right? All right. So, anyways, let's get into the hydrocarbon derivatives, right? So in this case, we have alkyl halides, and they include stuff like fluorine, chlorine, bromine, or iodine. And yeah, so with the naming, you like for the alkyl halides, they're just like the branches, like you put the branches right in front. So it's gonna be kind of simple, right? For example, like here are the two examples, right? One of them is chloromethane, and the second example is 1,2-difluoroethane. So basically, they become like ethyl branches, but now they're alkyl branches basically, but now like it's a halide name, depending on what it is, right? So next up we have alcohols, which are they are the OH groups. So the suffix for these is gonna be all, right? So the thing is, okay, so for multiple like hydroxyl groups, you have to keep the E in the parent name. For example, ethane 1,2-diol, right? But yeah. And then so with the naming, you have to give the lowest number. You always have to give the lowest number. So for everything we talk about, lowest number. Yeah, so if it's like not even multiple, it's gonna be like, it's a matter of if it's the number of hydroxyl groups is like a vowel, you can remove the E. So that's the thing. But like for any other multiple that's a consonant, for example, as in my earlier case, you're gonna keep the E in the parent name, right? So this, for one example with like without the E, it was gonna be like something like pentantuol, right? Look at that. Look, notice the naming. Okay, so yeah. Okay, so for carboxylic acids, they're the COOH. The suffix is gonna be oic, then acid, right? So yeah, for the parent, like you name it normally, except now for the ending, you remove the E, replace it with the oic. So for example, methanoic acid or butanoic acid, right? Okay, so, and they will also have branches, and branches are literally the same thing. They don't change. Okay, so yeah. Now for esters, they're formed from a reaction between an acid and an alcohol. So we're gonna have, so for esters, so basically you have to name the alcohol part first as an ethyl group, and then it's gonna be separate, right? And then for the carboxylic acid part, you replace the oic with the OH. So here are two examples: ethyl methanoate, methyl ethanoate, right? Notice what they look like. All right. So for for reactions, different reactions give you different products, right? So for example, addition reactions, it's basically where you react alkenes or alkynes with hydrogen to give you a saturated alkane, right? Because from the earlier mentioning of these aliphatics, the alkenes and alkynes are unsaturated, right? So now for substitution, it's gonna be an alkane plus a halogen. So they used to make organic halides. So you replace one of the H's with you replace one of the H's with like some sort of like with one of the halide ions, and then you form an acid basically. So the product. So this is what the reaction looks like. So the reactants are alkane and halogen. Products are halide and acid, right? So it needs a catalyst. Same for addition. Now for elimination, it's the opposite of addition. Yeah, it's gonna be the opposite. So it's gonna be something like an alcohol or a halide that's reacted to give you an alkene. So with this one though, the catalyst, unlike the earlier two where we don't really have to specify, for this one the catalyst is gonna be sulfuric acid, right? So now for esterification, from the earlier point, so it's gonna be an acid and an alcohol to produce an ester plus water. Yeah, you can also think of it like condensation basically, yeah? Now, let's get into the polymerization. Holy cow, polymerization, right? So, polymerization reactions are usually two. So we have addition and condensation. So where with addition, it's the monomers link via double bonds to give you bajillions of links. For example, polyethylene, right? And then for condensation, it's going to be linkage via like an amide or an ester, right? So it's linkage via like functional groups. So yeah. And this is what it's going to look like, right? Okay, so now for the applications, it's mostly used in refining, in oil refining, especially like in Alberta province, for example. And yeah, so for example, with physical separation, because that's basically what organic chemistry kind of is, especially with the reactions, right? We have fractional distillation, which separates like all like the different fractions by boiling point. Like, so basically, the most common thing here that's distilled is crude oil. So it basically gives you like all these products. Yeah, like yeah. So something else that's not really mentioned as much is solvent extraction. So basically it uses solubility to pull components out. So for this one, something off the top of my head I always remember, especially even from middle school somehow, I still remember this, but salt basically, like, you know, like seasoning salt, like table salt, whichever kind of salt. Obviously it depends, some salt is mined, but a lot of times some salt is also like extracted from ocean water, which is basically boiled to evaporate off the water and leave you with the salt, right? So yeah, and now we have chemical synthesis which it ties in especially to fractional distillation, yeah. So where chemical synthesis is used to make products, useful products from like some less useful ones, I guess. So for example, with cracking, where you break long chains into smaller ones. So this is the reaction that's gonna, this is an example of reaction, and basically it's really, cracking breaks long chains into smaller ones, right? Yeah, and Reforming is the opposite of that. So it's going to be rearranging small molecules into branched ones for more useful items too. Like in this case, we have high octane fuel, like used in race cars, like the one basically in the background of this entire video. So yeah. Anyways, that was probably like 15 minutes. Holy cow, 15 minutes of some purely organic chemistry and a bit of yap somewhere in the beginning. But yeah, hope this was concise enough. And yeah, y'all take care. I may be back, I may not be back.